I want you to imagine a scenario. You're sitting on your couch, you know, kicking back after a long day, and you've just tasked your highly advanced, state-of-the-art AI robot to fetch you a nice, crisp apple from the kitchen.
Oh, the classic robot butler dream.
Right, exactly. And you paid an absolute premium for this machine. It's loaded with the latest foundation models, incredible computer vision, like the absolute
Top
works.
of the line.
Yeah. So you watch it confidently march into the kitchen. It reaches out, perfectly grasps the handle of the fridge, swings the door open, reaches its mechanical hand inside, and its metal fingers just close on empty air because, well, someone ate the last apple.
Right, and this is where the whole illusion of intelligence usually shatters. Because
Mm-hmm.
instead of, looking around the fridge or turning to you and saying, hey, we're out of apples,
Mm-hmm.
the robot just stands there.
It just freezes.
Yeah, it completely freezes. It fails the mission. Or, which is honestly even worse, it might close the door, walk all the way back to your couch, and extend its empty hand. Like literally pantomiming a successful action and handing you a completely invisible apple.
Which is just, I mean, it's pantomiming because it's internal script, just fired off the command, grab apple now, and it didn't even bother to verify if reality matched its expectations.
Exactly.
Welcome to the Deep Dive. Today is Monday, May 18th, 2026, and our mission today is to figure out how we finally give AI the common sense to stop, look at an empty fridge, and ask, wait, what if the apple isn't there, before it just blindly acts.
It's a massive hurdle in the field,
Yeah.
and it's something that has stumped developers for years. But we are looking at a really groundbreaking paper today that tackles this exact issue.
Yeah, the research is titled Lifting Traces to Logic, Programmatic Skill Induction with Neuro-Symbolic Learning for Long-Horizon Agentic Tasks.
Quite the title.
It is a mouthful. But I have to say, my natural enthusiasm for this stuff is always high because AI is evolving so ridiculously fast. I mean, it feels like every single week we get a headline about a model that can write a symphony in seconds, right? Or like ace the bar exam with flying colors.
Oh, absolutely. The cognitive leaps are huge.
But then you ask that same brilliant model to make a simple cup of tea in a virtual kitchen, and it somehow manages to burn the virtual house down. Why is there such a massive disconnect between, intellectual knowledge and physical execution?
Well, it fundamentally comes down to the difference between answering a static question and executing what researchers call long horizon planning.
Oh, okay. Long horizon plan.
Yeah. Think about it this way. Foundation models, like your large language models, are incredibly good at retrieving information and generating text in a vacuum.
Right.
But when you drop them into an unpredictable environment, whether that's a physical kitchen in your house or, a complex digital e-commerce website,
Hmm.
they are notoriously terrible at completing multi-step tasks.
Look, because things change.
Exactly. The environment changes, things aren't where they're supposed to be, and their transient prompting-based reasoning just completely evaporates.
So we understand the robot failed to grab the apple, but why exactly do current top-tier AI models fail at this? If they can pass a medical exam, why do they freeze in a kitchen?
The fatal flaw in current methods, and by current I mean the state-of-the-art baselines that are considered the gold standard right now for AI agents, is that they rely on what the authors call state-blind parameterized scripts.
State-blind scripts.
Yeah. Essentially, the AI agent distills its past experiences into a really rigid memorized sequence. It learns a linear script, like go to fridge, then open fridge, then pick apple.
Okay, I have to push back here for a second because we're talking about large language models that are remarkably sophisticated. I mean, they can read and write complex Python code. Why can't they just read a recipe and adjust on the fly if something goes wrong?
It's a totally fair question.
Why do they act like they have blinders on?
Well, you have to think about the computational and cognitive load happening behind the scenes. When an LLM generates an essay for you, it's predicting the next word based on a static prompt that isn't changing.
Okay, sure.
But in a physical or digital environment, the prompt is the state of the world, and that state is constantly updating every single second.
Right.
So to adjust on the fly, the model would have to perfectly reevaluate the entire history of its actions, plus the entire state of the room, at every single micro step.
Oh, wow. That sounds exhausting.
It is. Over a long task, that context window, which is basically the AI's short-term memory, gets totally cluttered with noise.
Mm-hmm.
The prompt history gets too long, the AI gets confused, and the reasoning chain just snaps.
It's like a friend trying to bake a cake by following a script while completely blindfolded. They have the steps memorized perfectly, like reach for it, grab the bag of flour, pour out 1 cup.
Yeah, blindfolded baker.
But if you sneak in and move the bag of flour just 2 inches to the left, they'll confidently scoop empty air, dump that air into the mixing bowl, put it in the oven, and then wonder why the cake tastes like nothing.
That is a phenomenal analogy. They are acting without observing.
Right, they have the raw intelligence, but they lack the sensory grounding to reality at the exact moment of execution.
Exactly. And the paper actually quantifies exactly when that blindfolded baker gives up. The researchers ran a survival analysis on those gold standard baseline models we mentioned earlier,
Okay.
and they discovered a phenomenon they called the long horizon collapse.
Oh, that sounds incredibly dramatic, the long horizon collapse.
It is a dramatic failure. They found that around the 22-step mark in a complex task, these baseline models just hit an absolute brick wall.
22 steps, that's it.
That's it. Their reasoning errors accumulate in that cluttered context window to the point where their success rate plummets to absolute zero. If a task requires 23 steps, the baseline agents literally cannot complete it.
They just break.
Yeah, they get lost, they start hallucinating actions that don't make sense, or they just get stuck in endless repeating loops.
So if blind memorization leads to an inevitable 22-step collapse, how do we give the AI its eyes back? Like, how do we force it to check for the apple before it closes its hand? Okay, let's unpack this,
Right.
because this is where the paper introduces its big solution, right? NSI, or Neuro-Symbolic Skill Induction.
Yes. NSI is a complete paradigm shift in how we structure artificial reasoning. Instead of memorizing a blind script, NSI takes the agent's interaction, traces its past successful experiences, and lifts them into modular, logic-grounded programs.
Okay.
It effectively gives the AI what we can think of as two distinct halves of a brain.
I love that framing. The two halves. It sounds like we have a creative side and a logical side.
That's a really great way to look at it. First, you have the neural module. This is your large language model, and it acts as a semantic perceptor.
So it's looking at things.
Right. Its job is to look at the messy, unstructured environment like a camera feed of a messy kitchen or the raw, chaotic HTML code of a web page and parse all that noise into structured, updated facts.
So the neural part is looking at the fringe and explicitly updating a neat little internal fact sheet that says, fact, fridge door is currently open, fact, apple is not inside the fridge.
Precisely. It translates the messy world into clean data. And then you have the second half, which is the symbolic module.
The logic's there.
Exactly. This is the execution graph, and it is written in strict first-order logic. Now, first-order logic is basically an inflexible mathematical rulebook. It deals in absolutes, true or false, exists or doesn't exist.
So there's no guessing.
Absolutely zero room for hallucination here. The symbolic graph takes those clean facts provided by the neural module and uses them to navigate explicit, hard-coded decision trees.
And what's really fascinating is how NSI actually goes about building these decision trees, because it doesn't just use a toolbox of static, predefined tools that a human gave it, right? It actively invents its own logic nodes on the fly.
It does.
The paper details 4 specific logic-grounded operators that make up the symbolic brain, and they sort of flow together like a story.
Let's follow that story. So the AI knows it wants an apple, but before it can grab it, it has to physically locate it. That's where the first operator, the data op, or data operation, comes in.
Right, so instead of the script just blindly firing a pick apple command, the data op forces the AI into a think then act logic.
Yes.
It synthesizes a mandatory step that basically says, hey, search the current state of the room for an object that fits the description, apple, and explicitly bind its coordinates to a variable before you do anything else.
Exactly.
It forces the robot to find the apple with its eyes before it is mathematically allowed to move its hand.
It guarantees that the arguments for an action actually exist in the physical world. But let's say the data op finds the apple, but the apple is behind a closed fridge door. The AI can't just reach through solid metal.
Right, that would be a problem.
That friction point gives birth to the control op, which includes checkups and loop ops. These act as the decision boundaries.
And this is where the AI really starts to mimic human branching logic, doesn't it? A checkup introduces a literal if-then statement based on the environment.
Yes, exactly.
Like, if the fridge is closed, then execute the open door command. ELSE, proceed to reach inside. It's giving the AI the ability to make forks in the road based on reality.
And once those forks are navigated, once the data op has found the variables, and the control has ensured the path is clear, then comes the primitive op.
The actual movement.
Right. This is the actual grounded action execution, the physical movement. Robot arm moved to apple.
And it doesn't just stop there, which is the problem with older models. It finishes with the terminal op. This is the execution feedback.
The status report.
Yeah, when the movement ends, the AI demands a status report. It returns a definitive success, or, and this is the crucial part for learning a specific failure diagnosis, like target not found after navigation.
What's fascinating here is that this neuro-symbolic architecture perfectly mirrors human cognitive psychology. Specifically, it maps beautifully onto the transition from System 2 to System 1 thinking.
I am so glad you brought that up. For anyone who hasn't read Daniel Kahneman, System 2 is that slow, deliberate, incredibly exhausting step-by-step reasoning.
Right.
It's like when you first learn how to drive a car, you are actively thinking about the pedals, the mirrors, the steering wheel. That's your LLM trying to calculate probabilities and prompt its way through a task from scratch every single time.
Yes, and doing that over a long period is computationally exhausting and incredibly prone to error, which is why that 22-step collapse happened.
If it's too tired.
Exactly. Now, System 1, on the other hand, is fast, reflexive muscle memory. It's you driving home from work on autopilot. NSI takes that slow, exhausting System 2 reasoning, figures out the correct path, and compiles it into a fast, executable System 1 program graph.
Oh, wow.
But because it uses those data and control operators, it maintains rigorous logical safety checks. It is muscle memory, but it's muscle memory that still actively looks where it's going.
Okay, so NSI uses this incredible flowchart system, this highly evolved neuro-symbolic brain. But how does it actually build these flowcharts?
That's the million-dollar question.
Because a human programmer isn't sitting in a cubicle somewhere typing out every single step and if-and statement for every possible kitchen layout in the world, right?
Oh, if a human had to hand code all of that, we'd be right back in the dark ages of brittle expert systems that break the second a chair is moved out of place.
Right.
NSI builds these logic graphs completely autonomously through a two-stage offline induction process. The authors call it progressive specialization to generalization.
That is a mouthful of academic phrasing, but the underlying concept is actually super elegant. Stage 1 is intra-trajectory consolidation. Essentially, the system looks at a single successful demonstration trace, let's say. One time, a robot successfully got an apple out of a specific fridge, and it synthesizes a local expert graph that perfectly replicates just that one specific success.
Right. It identifies the critical state changes and writes a piece of logic to mirror it. But, as you can imagine, a highly specialized tool that only knows how to get an apple from that specific fridge on that specific day isn't very useful in the real world.
No, not at all.
So stage 2 is inter-trajectory merging. The system takes dozens of those local experts from different demonstrations and structurally merges them into a single, highly generalized global skill.
And it does this guided by something called the minimum description length principle, right?
Exactly.
I want to make sure we define the minimum description length principle because it sounds intimidating, but it's basically Occam's razor applied to data compression.
That's a good way to put it.
The AI is trying to find the simplest, most compressed way to represent all these different successful paths without overfitting to one specific kitchen. It basically wants to strip away all the noise.
You've got it. It is optimizing for maximum empirical consistency, meaning the logic holds up in all the observed scenarios while minimizing the actual complexity of the code.
And the tools the LM uses to compress and combine these graphs read like a story of an AI generalizing its understanding of the world. There are 4 structural operators here.
Let's hear them.
Let's say the AI knows how to open a door, but now it needs to learn how to adapt. First is conditional branching.
Yeah.
If one memory trace had a fridge with an open door and another trace had a closed door, the system sees the conflict.
Right.
It literally invents an if-then guard condition where those 2 paths diverge, resolving the conflict.
Then there's modular crossover.
Yeah.
Because the AI skills are represented as independent nodes on a graph, the system can actually graft a useful piece of logic from one skill directly into another.
Oh, that's smart.
Yeah, if it spent hours learning how to carefully navigate around a kitchen island in a cleaning task, it doesn't have to relearn that. It can just copy-paste that spatial logic node into a completely different cooking task.
It's literal code recycling. And then there's variable lifting, which is honestly my favorite part because it shows true abstraction. The paper has a great example here.
The sink example.
Yes. Imagine the system has one memory of washing an apple in a kitchen sink. And it has another memory of washing a frying pan in a bathroom basin.
Okay.
Instead of hard-coding the nouns sink or basin, the system analyzes the properties of both. They both supply water, they both have drains, and it lifts them into a generalized parameter, a washable station.
That's the abstraction.
Right. So now the agent can walk into a totally new room, see a plastic bucket full of soapy water, and realize, that fits the parameter of a washable station. I can use that.
It successfully abstracts away the specific nouns to understand the broader functional category. And the fourth operator is loop folding.
Okay, what's that?
Well, if the agent observes a trace where it had to check 5 different drawers to find a missing knife, it doesn't write 5 separate clunky check drawer commands. It turns that repetitive, noisy action into a single, compact loop node. Check drawers until knife is found.
It's brilliantly efficient. But, as we all know, even the most beautifully compressed, efficient plans fail when they hit the chaos of the real world.
Always.
A robot could have the perfect generalized flowchart for getting a snack, but what happens when our newly minted NSI agent encounters an entirely new obstacle? Let's say someone put a child lock on the fridge door.
That is the true test of autonomous intelligence.
Yeah.
When a normal baseline script hits a child lock, it tries to open the door, fails, doesn't know why, and just crashes.
Yeah.
The task is over.
Here's where it gets really interesting, because when NSI fails, it refuses to just crash. Remember that terminal loop we talked about, the feedback loop?
Yes.
It returns a symbolic diagnosis. It tells the agent, hey, I tried to execute the open fridge logic, but the state of the fridge is still closed. It provides the exact mathematical reason for the failure.
And that failure diagnosis triggers what the authors call reflective planning. The agent reads that specific error. It realizes its high-level System 1 skill graph does not have a branch for a child lock.
Right. It's never seen one before.
So it temporarily drops back down to raw, System 2 reasoning. It looks at the environment, analyzes the plastic lock, and tries to use atomic actions to solve the puzzle.
It basically says to itself, okay, the script failed. Let's look at this weird plastic thing. What if I squeeze these 2 tabs and pull?
Exactly, it experiments. And if the agent successfully recovers, if it figures out the tabs, gets the child lock off, and opens the door, it performs something called skill honing. And this is the self-evolution part.
This is the part that genuinely gave me goosebumps. It takes that successful raw recovery path that it just figured out on the fly, and it literally grafts it onto the failure node in its own skill graph.
It updates itself.
Yeah, it adds a brand new branch to its own source code.
This raises an important question about the nature of these systems. The agent is fundamentally turning transient runtime errors into permanent capability upgrades.
Wow.
It encountered a frustrating edge case, puzzled it out once using heavy computation, and then rewrote its own underlying logic. The next time it sees a child lock, it doesn't even have to think about it.
It just opens it.
Right. It doesn't use System 2.
Yeah.
It just effortlessly executes the new System 1 branch. It repairs its own logic without forgetting the parts that already work.
That is wild. It's essentially coding its own software patches in real time. So this all sounds amazing in theory. The architecture is beautiful, the self-evolution is incredible, but we need to look at the data.
Always look at the data.
Does it actually beat the 22-step collapse we talked about earlier?
The empirical study in the paper is incredibly rigorous. They didn't just test this in one scenario. They tested NSI across 3 completely distinct domains to prove it wasn't just a parlor trick fine-tuned for one type of environment.
And looking at these benchmark results saying they crushed the baselines feels like a massive understatement.
Oh, absolutely.
They tested it in ALF World, which is your household embodiment stuff, navigating virtual kitchens and living rooms. They tested it in WebShop, which is a highly cluttered, simulated e-commerce platform. And TextCraft, which involves complex crafting tasks in Minecraft.
Right.
Let's look at the ALF World jump specifically. The absolute state-of-the-art baseline model achieved a 70.6% success rate. NSI achieved a 98% success rate.
It's unbelievable.
98%. It basically solved the benchmark entirely.
And if you look at WebShop, which is incredibly noisy and dynamic, I mean, think about how frustrating it is for you as a human to navigate a website with pop-ups, changing layouts, and weird search filters.
That was a nightmare.
The baseline AI gets totally lost there, scoring a dismal 7.7%.
Wow.
But NSI scored 76.5%. It is an order of magnitude better at navigating digital chaos.
But I want to dig into the computational why here. Obviously, it's winning definitively, but looking at the math, I have to assume it's because it's no longer getting bogged down in the micro details.
Right.
If you don't have to think about exactly how to bend your fingers, you can just focus on washing the apple right. How is it destroying the competition like this?
You're exactly right. And it goes back to solving the 22-step collapse
Mhm.
through a concept the authors call horizon compression. When you look at the skills NSI generates, it encapsulates an average of 7.4 atomic actions into each modular skill node.
Let me make sure I understand the mechanics of that. So finding a sink, turning on the cold water, placing the apple under the water, scrubbing it, turning off the water. That's maybe 6 or 7 individual atomic steps.
Right.
But NSI packages all of that into one unified wash item skill.
Yes. And computationally, that changes everything. Because to the high-level LLM planner, invoking that complex, 7-step physical routine only counts as 1 step of reasoning in its context window.
Oh, that is so clever.
By doing this, NSI effectively compresses the planning horizon. The AI's short-term memory doesn't get cluttered. A massive task that normally takes 50 atomic actions, which would completely overload a baseline model's prompt history and guarantee a collapse, only requires the NSI agent to make maybe 7 or 8 high-level skill decisions.
That makes perfect sense. It drastically reduces the noise in the prompt history. It shifts the burden from fragile micromanagement, where the AI is constantly worrying about every finger twitch, and losing the plot to robust macro execution.
Exactly.
It's just thinking, go to kitchen, wash apple, bring to human.
And because of this profound compression of the context window, the survival analysis shows NSI completely ignores the 22-step collapse. It sustains valid, error-free execution up to 53-plus steps without any spike in planning complexity.
It just keeps going.
Yeah, it calmly executes its logic-grounded graphs without getting tired or confused.
So what does this all mean? Let's zoom out for a second and look at the whole journey. We started with a wildly expensive robot completely freezing because a single apple was missing from a fridge.
Right.
And NSI takes that brittle, blind script reader and transforms it into an adaptable, self-evolving architect of its own logic. It looks at the world, it thinks about the rules, it acts, and if it fails, it rewrites its own code so it never fails the exact same way twice.
If we connect this to the bigger picture, we really have to look at the impact statement provided by the authors at the end of the paper. On one hand, achieving resource-efficient AI development without requiring armies of human programmers to manually engineer rules for every conceivable environment is an incredible leap forward.
It's a game changer.
The agents adapt themselves to our messy reality. But, as the authors note factually, these highly capable self-evolving agents could be utilized for unintended purposes.
Right, because if an agent is this exceptionally good at autonomously navigating complex, chaotic digital environments like web shop, it's also going to be very good at navigating, say, secure databases or private corporate networks if given a malicious goal.
Precisely. The ability to autonomously analyze and bypass novel obstacles, like our child lock example, is fantastic when you want an AI to finish your household chores.
Sure.
But it presents a significant security challenge if the agent is actively trying to bypass digital authentication or a firewall it hasn't seen before. The authors emphasize that this paradigm shift necessitates robust safety alignments that can operate at the same logic-grounded level as the agents themselves.
It is a brave, deeply fascinating new world, and I want to leave you with a final thought to mull over, something that really struck me after reading about how this system self-evolves. We have always historically thought of software as static. It's a tool that a developer builds, we deploy it, we use it until it breaks, and then we wait for the developer to push an update to fix it. But here we have an AI that encounters an obstacle like a child lock, decides on its own to drop into a problem-solving mode, rewrites its core programming to bypass it, and commits that new code to its permanent memory.
It's truly unprecedented.
And if that self-coding machine makes a mistake during its real-world experimentation, let's say it accidentally breaks the handle off your fridge while testing how to open the child lock, whose fault is that?
That's the million-dollar question.
You didn't program it to rip the handle off. The original developers at the tech company didn't program it to do that. The AI wrote the experimental code itself in real time. At what point does a machine that dynamically writes its own operational logic become legally and practically liable for the consequences of its own muscle memory?
It fundamentally challenges our entire legal and conceptual framework regarding tool ownership and liability.
Think about that the next time you ask your robot to check the fridge.
Thank you for joining us on this deep dive into the architecture of self-evolving AI. Keep questioning, keep exploring, and we'll see you next time.